lim super n. Got it. Okay, so we have this identity, and as you see, Bn is an increasing sequence, okay, and it is equal to whole space almost everywhere. So if I take, if I take any omega in Bn for a fixed n, then I know from this that by definition of Bn xn plus 1 of omega minus xn of omega is less than epsilon n. Okay? Now, as we know that Bn is an increasing sequence, since Bn is a subset of Pk for k greater than n. Hence, this implies also that since omega belongs to Bk, we have also xk omega minus xk plus 1 of omega is less than epsilon k by definition of Bk. Okay? Hence, for this omega, we have sum from nth rank on to infinity xk of omega minus xk plus 1 of omega. This sum is convergent because epsilon k's are convergent. Okay? And this is true for any omega in Bn. Now, let me choose any omega. So let omega be in the union of Bn's from 1 to infinity. Then it will be in some Bn, okay, because it covers all the space, almost surely, of course. Then let's look at the limit as n goes to infinity of xn of omega. Okay, so it will, I can write this limit as n goes to infinity of xn of omega minus xn minus 1 of omega plus xn minus 1 of omega. I add and subtract same thing, minus xn minus 2 of omega plus xn plus 2 of omega, etc. xn minus 2 of omega minus xn minus 3, etc. And this goes up to x1 of omega. Hence, this is equal to then x1 of omega plus sum n greater or equal to 1 xn plus 1 so limit n here, of course, after this limit. Okay, there is a limit here. So xn plus 1 of omega minus xn of omega. Since then omega will be in Bn, so these things will be all less than epsilon n in absolute value. Hence, this means that this sum is convergent. Hence, the limit exists. Hence, limit exists of xn exists. That's exactly what we are saying, because pointwise limit of measurable random variables is measurable. Okay, so this is the most general convergence theorem almost everywhere in probability. I will use this to show you some very difficult results very easily, combining this with dominated convergence theorem. That's why I am doing these things in detail, because it gives very nice examples of application. So let me give some elementary results about the convergences. First is that almost sure convergence is stronger than convergence in probability. Proof is easy. I have to show that limit as n goes to infinity for any positive epsilon, probability that xn minus x greater than epsilon is 0. I have to show that if this thing is 0, okay? But this is less than or equal to limit as n goes to infinity of probability of the union k greater or equal to n of the set such that xk minus x greater than epsilon. Okay, because this set is always smaller than this huge union. And since this is a decreasing sequence with respect to n, I can put the limit inside. You see where we use the sigma additivity of a probability. This is indispensable. Otherwise, you cannot pass to the limit in the calculations. So this is equal to, I put the limit inside. This is equal to probability of the intersection and union k greater or equal to n xk minus x greater than epsilon. And what is this? This is less than or equal to, from lemma that we have written, probability of the lim sup as k goes to infinity or n goes to infinity, doesn't matter, xk minus x greater than epsilon. But this set is empty because I know that xk converges to x almost surely, hence lim sup is also has the same limit. So this thing is equal to 0. 0 greater than epsilon is empty set, hence this is 0. So this shows you that you have convergence in probability if you are given convergence almost everywhere. Okay, another exercise is another theorem. Of course, we have seen that convergence in probability is bigger than convergence almost everywhere. Nevertheless, if we have convergence in probability, convergence to x in probability, then we can choose a subsequence which converges almost surely. Then there exists some x and k such that limit as k goes to infinity, x and k of omega is equal to xp almost surely. This is also important because it will give me an extension of dominated convergence theorem. Okay, the proof is easy. I will use theorem C. Now I choose a subsequence x and k in the following way. First, I will take n1 is equal to 1. Okay, and then nj I will define as the infimum of the capital N's after nj minus 1, such that probability xr minus xs greater than 1 over 2 to the j is less than 1 over 3 to the j. This is for, so I choose, and this should be true for any r and s greater or equal to n. Okay, so higher the n is, capital N, then I have to choose higher indices by hypothesis. Okay, so this is an increasing sequence, and if you choose then ng is like that, then you look what happens. Probability then x and j minus x and j plus 1 greater than 1 over 2 to the j is less than 1 over 3 to the j, and this sum is convergent. Okay, 1 to infinity, 1 to infinity, and this is finite. Hence, this theorem that we have just proven, theorem C, implies that x and k converges to x almost surely. Why to x? Because I know that x and k converge to x in probability already, and as x and k converges also, as x and k implies convergence in probability, the limit should be same. Okay. should be same in probability or almost sure. Because of the preceding result that if, let me explain, if x and k converges to a random variable y, almost surely, and this implies that x and k converges to also y in probability, but I know already that x and k converges to x in probability, hence x is equal to y. Okay? Is it okay or not? Are you sleeping?
Okay, hocam.
Okay.
We are here, not sleeping.
Huh?
We are here, not sleeping.
Okay. So, another theorem about the convergences. If xn converges to x in L1, then this implies that xn converges to x in probability. This is easy because we use just Chebyshev inequality, which says that probability xn minus x greater than epsilon is less than or equal to 1 over epsilon times expectation of xn minus x, and the latter goes to 0 as n goes to infinity, period. Okay, so this is nothing deep. Now, let me give a fine result which says that, in fact, this is an extension of dominated convergence theorem. This is dominated convergence theorem plus. Plus means extended. Okay, now, so what was the dominated convergence theorem? We have convergence pointwise or convergence almost everywhere to a random variable if all the elements of the sequence are in absolute value bounded by an integrable positive random variable, then the convergence takes place in L1. Okay, so the initial convergence was convergence, pointwise convergence, so everywhere. We can replace it with convergence in probability, which is bigger. This is the extension. So if xn converges to x in probability, and if they are all bounded they are all bounded in absolute value by a random variable in L1, positive of course, almost surely, then xn converges to x also in L1. Okay, so this is a very nice result, and this is one of the most important results when you use this in the calculation of very delicate parameters, etc. in applications. I shall show you several examples of this. Okay, the proof of this. First, as xn converges in probability to x, I know that there exists a subsequence xn k with convergence to x almost surely. And since they are all bounded by y, this implies from the initial dominated convergence theorem that xn k converges to x in L1. Hence, in particular, x is also integrable. Okay, and let me now show that expectation, so it remains to prove that limit as n goes to infinity, expectation of xn minus x is equal to 0. Not xn k, but xn. So we are taking the larger sequence, okay? So this is the challenge. Well, we write it, we take expectation of x minus xn. So we write it as the sum of x minus xn on the set on which this thing is greater than some epsilon over 2. Epsilon is any positive arbitrary number plus same thing, xn minus x on the complement of the first set. Okay, so already the second set is less than or equal to epsilon over 2. So this is less than or equal to epsilon over 2 plus, then since xn and x are all bounded by y, this thing is less than or equal to twice expectation of y times indicator of the set xn minus x greater than epsilon over 2. Okay, so I didn't do anything delicate here. Here, then I claim that since xn converges to x in probability, this set has a small probability for large n, and y is integrable. Hence, I can choose n sufficiently large in such a way that the probability of this set is less than delta, in such a way that expectation of y times indicator function of this set is less than epsilon over 2. Let me do it as a separate lemma. So if then y is the same thing, then okay, there is no, if for any positive epsilon, there exists a delta positive such that if probability of A is less than delta, then this implies that expectation of y times indicator of A is less than epsilon over 2. This is the challenge, okay? Now, proof of this is very easy. Since y is integrable and positive, from dominated convergence theorem, expectation y times indicator function y greater than n, this goes to 0. This is monotone convergence theorem. Because this thing decreases to empty set, hence this thing decreases to 0 pointwise, and then I commute expectation with limit. Okay, so this is one line proof. So then this implies that expectation y times indicator of A can be written as expectation of y indicator of A intersection y greater than n, plus same thing, expectation of y indicator A times y less than or equal to n. Okay, so the first one, this goes to 0 because, okay, let me write it again. One step. I will not do this all the time in detail like that, but these things are important. Y greater than n, plus then expectation of y indicator A intersection y less than or equal to n, and this thing is small, less than or equal to, since this goes as with n, this goes to infinity. For large n, this is less than or equal to epsilon over 2 for large n. For n large, plus here we have n times y is less than n, hence I replace y with n here, so I put n here and I forget this, I take probability of A. So if I choose probability of A less than epsilon over 2n, then we are done. Hence, with this choice, we obtain that this thing is also less than epsilon over 4 with 2. So I have choose here something for n. Okay, hence this gives you here less than epsilon, and this is exactly what we are trying to do. Okay. Let me give an application of this stuff. This is one of the most beautiful results of mathematics. It's called strong law of large numbers. I will give you in a case which is at the same time it requires high integrability, but very general in the sense that you don't need to take the random variables of the same law. So application this is strong law of large numbers. These are the initials. Okay, so you have well, they are used worldwide. Okay. What is strong law of large numbers? Let me explain it. We are given a sequence of random variables, xn, a sequence of real random variables which are independent. Independence in the elementary probability sense. Okay. Did you see it or not? I hope yes.
Yes. Now we know.
Good. So I will suppose that their expectation, okay, they are integrable. All integrable. And their expectation is constant. This is constant equal to expectation of x1. Then, and assume this is a strong hypothesis, but nevertheless, it is very valuable. Supremum with respect to n, expectation of xn absolute value to the power 4 is finite. This is the hypothesis. Then the set of omegas such that limit as n goes to infinity, 1 over n, sum from 1 to n, xi of omega is equal to expectation of x1 is equal to 1, this probability. So, as you see, the limit is inside the probability. This is much more difficult and much more important than the weak law where the limit is outside. What does it mean? It means that when you are making a simulation, if you have these conditions, the probability of beginning on the good omegas, which gives you the good result of the simulation, has full probability. Especially, for instance, when you want to simulate the work of a computer network, or I don't know, choose anything from artificial intelligence, whatever you want, then you are on good probability points. Okay, this, without this, we cannot survive technologically. This is really the basis of Monte Carlo also. This is the ancestor of simulations. Okay, everything in technology depends on this theorem. So here, so when imagine you are doing this with coin tossing, for instance. Okay, so you are given a set 0, 1 representing head and tail, and if you have an experience of length n, so your probability space will be this set. This is an n-dimensional set. So you take the probability on this set, you look at this, then you take the limit as n goes to infinity. This is called weak law of large numbers. But what we do is we are first taking the limit with respect to n, then we are looking at the probability. So it means a priori that you have a probability on the space 0, 1 to the infinity. Okay, this is totally, tremendously different. This has nothing to do with elementary probability there, which is taught in the universities in Turkey. Okay, but this is here, the real technology is, at stake. So this is just for you to understand the importance of this result. and the difficulty that it requires. So you cannot teach this to the students saying that there is a probability on the space. They will say, how do you know? Well, that is here the grandeur of Kolmogorov enters in game. Kolmogorov and then Prokhorov theorems. They give how to construct a probability on an infinite product like that. In fact, we shall use infinite dimensional things like R to the infinity, countable infinity, which is ancestor of all the big large spaces. This contains continuous functions on 0, 1 in particular in some certain sense. Okay, hence Kolmogorov theorem is valid on this, so we are in good situation. But this has required at least 2 centuries of research. Okay, so let us, maybe I will stop here, and I would like you very much that you read this convergence hierarchical results in such a way that next time I will give a very nice example of this through some ergodic theorems. Okay, for instance, I will calculate as an application I will do the following. Let f and g be 2 continuous functions on 0, 1. And suppose that g is strictly positive. Okay, so I will calculate limit as n goes to infinity of some integral on 0, 1 to the n of sum of xi dx1, this is 1 to n, this is multiple integral of order n, then I am taking limit and I am dividing this with the same thing here, n, 1 to n, g of xi's, you sum them and you integrate dx1 up to dxn. I will calculate this limit using these things and dominated convergence theorem. You will see, for instance, here there is no probability at all at the beginning except the Lebesgue measure on 0, 1. Okay, and nevertheless, I will use probabilistic considerations to prove this. Ask this to a pure mathematician who doesn't know probability, he'll go crazy. Okay, I stop here.